Hi, I'm here today to talk to you about tips and tricks on the Amplify 8th grade science magnetic fields unit for their Waterwheel Flextension. At Jane Addams, we've been doing this Flextension for a few years, so there's some stuff we've learned and some stuff I can pass along to help make this activity a little more seamless for you on your end. One thing to note is that this activity has kinetic energy transforming into potential energy, whereas in the magnetic field sim, it's potential energy transforming into kinetic energy. But this is a really good way to build upon the harnessing human energy unit. And so students should be able to see that while the energy transformation is the reverse, it's still equally applicable. I brought a couple of my students' finished designs. They did get slightly crushed in my bag bringing them home, but you'll be able to see kind of what they're doing. The materials we provide each student are a water bottle with a hole that we have pre-drilled in the bottom, some string. The amount of string doesn't really matter too much. It's not something you need to control per se, because you'll be measuring the change in height and string length doesn't matter there. Some tape, both to tape the string onto the bottle as well as tape any wings or fins onto the bottle. A weight at the end. Amplify suggests using washers, but since we were in the magnetic field unit anyway and we didn't have washers, we use these nice circular magnets. You can also use bolts or anything lying around that you have. It's simply a weight that you are raising with your water bottle. And a skewer here. So each group needs a skewer if they want to kind of practice a little, but if you're short on skewers, you can also have 1 or 2 testing stations and they share the skewers. And then cardstock. We give our students 3 pieces of cardstock per group and about 1 meter of duct tape per group. You want to use duct tape or packing tape because those are both waterproof tapes. If you're using Scotch tape or masking tape, this is going to fall apart the second water hits it. I do make sure that I do per group, because as it is trying to find 80 water bottles, especially, you'll notice these are different sizes. I do try to make control variables per class period. So I would have like 8 of these per class period or 8 of these per class period, just to try to control the water bottle size that kids are getting. The reason I limit the tape and do per group is because, as you know, kids will eat tape if given the chance. So they get exactly 1 meter of tape and it is per group. And that way you don't have to buy rolls and rolls of tape. And then the cardstock, 3 pieces of cardstock is more than enough for most groups. Most groups actually only use 2, but I like to be really generous. And then students obviously need scissors, access to scissors, so that they can cut the cardstock any way they want. So if you follow the Amplify Flextension directions, they're pretty self-explanatory. However, there were a couple of tips that I did want to show you. So a couple of tips are, when you are drilling the holes, so you can see the hole is drilled right there, I recommend you drilling them with the cap on. That keeps a certain amount of air pressure inside the bottle and allows for easier drilling. The other thing, and this should be obvious, but of course it never is, make sure that you drill a hole large enough for your skewer to fit through so that the bottle can turn easily. It's really important, and this is in the directions, but I'm just going to highlight it, that students tie the string and then also tape it on. That way the string can't move around the bottle, right? Because if the string moves around the bottle, then it's not hoisting anything up. And it's important that they do that on this side. So like on the bottle side of the little lip here. The other tricks have to do with how you're going to test your water wheel. If you use this image here from Amplify, it makes it look super, super easy, and it is not actually the case. So this clearly makes it look like you need one person to test it and everything goes off without a hitch, and hey, just test it into a bucket and everyone will be happy. I find that really you need about 4 people to test it, which is also why I would do this as a group instead of an individual. If you have sinks in your room, this is the setup that I make, where I tape a meter stick to the side of the sink with 0 down here. And then kids actually test over the sink. They're not using the faucet. The 2 main control variables that I insist on are that, 1, that they should be testing with 200 milliliters of water, and then 2, that they should all be testing 15 centimeters above their water wheel. So meaning that they are holding the water 15 centimeters above their water wheel when they pour it, which does mean they need a separate ruler. So realistically, you need 4 people to test this. So you need 1 person to hold the water wheel, 1 person to pour the water, 1 person to measure where the weight starts and stops, and then 1 person to actually measure the 15 centimeters so that the person knows where to pour it. A couple of tips. One is that when you hold this, you want to tilt it slightly upwards so that when the string starts to coil up, it coils up around the water bottle. If you're holding it level or even down a little, the string has a tendency to get caught around the skewer, and then it can't pull. You'll notice as it goes, it can't pull the string up, and in fact gets tangled and stops turning. I tell my students if this happens, then they need to start over and take that trial again. That shouldn't count as anything because the string didn't go up. Another tip is that you want to have somebody, whoever's measuring where the string starts and stops, or where the weight starts and stops, you want to make sure that when it stops moving, you have them catch the weight at the bottom, because you've now piled up all this potential energy. The first thing that's going to happen is it's going to go and spin back down. And so you want somebody to catch the weight to see where it actually ends, so that you can calculate that change in height. A couple of extensions that you can do with this activity are you can showcase the water wheels before testing, so students can develop hypotheses on which water wheel will be the most efficient at converting the kinetic energy of the falling water into the potential energy of the weight. That's also why it's kind of nice to do with groups, so you don't have 30 different water wheels that people are kind of looking at. If you want to bring in variables, I've already talked about control variables of the height from which you pour the water and the amount of water. Then you can talk about independent variables as the wings that they have engineered. You can have students do repeated trials, but you do want to be aware that once some of these wings get wet, they're going to kind of fall apart. So you can either coach them through that at the beginning, telling them to use a little more tape to keep their wings a little waterproof, or you can use that as a great place to improve at the end. It's your choice. To bring in some math, you can have students graph the averages of theirs and maybe 3 other groups, or even the whole class. You could have them write a CER answering the question of which water wheel was most efficient at converting kinetic energy to potential energy, with the understanding that the highest change in height is the highest increase in potential energy, which they should know a little bit already from harnessing human energy. And for those of you who incorporate going further activities into your class, you can actually have them calculate the potential energy increase and then use that if they're writing a CER. In order to calculate the potential energy increase, they're also going to need to convert the mass of, they're going to need to calculate and then convert the mass of their magnet into kilograms, and convert the centimeters as change in height into meters, which I think is a really good extension, especially using math for students to do, since really converting between metric units isn't taught very concretely ever until they get to higher level science where teachers just sort of assume they've learned it. So I sort of see converting between metric units like learning a language. The earlier you start, the more it just becomes second nature. Please feel free to reach out to me if you have any questions on how I use this or any of the things I've talked about that you're a little confused about, so that I can help answer those before you get into using it with your kids. Have a great day.